Okay, so let's start with the first problem. We have an 80% stress-free Guijo wood is used as a joist to support the following loadings in a residential house. So meron tayong given dead load and live load. And we have here, as a dead load, meron tayong flooring and self-weight equals to 500 pascals daw or equivalent sa Newton per meter squared. So pressure siya, no? Then we also have a ceiling and ceiling joist for 250 Pascal. And then we have partition wall for 80 Pascal. So may i-consider tayo ditong tributary width, no? To consider this portion ng area na pwedeng sakupin ng flooring na sinusuportahan dun yung design na joist natin. Then we have live load. This is based from, I think, UBC, no? Then for residential, nakalagay sa kanya is 2.0 kilopascal or 2,000 Pascal. Okay? So the question is, if the joists are spaced at 300 millimeters on centers and has a span of 3.6 meters, what will be the most adequate section? Meaning, will satisfy yung ating four requirements, which is bending, shear, deflection, and yung lateral stability, and assume an allowable deflection of L over 300. Okay, so what to do first is to at least conceptualize kung anong itsura nung ano natin, nung mismong structure na din-design natin. So let's say ito yung ating sabihin natin ito yung ating joist. Okay? Na lalagay natin. Okay? Then let's say meron siyang nakapatong sa kanyang flooring system, no? Yun yung para sa flooring niya. So assume natin na may flooring siya dito at top. Okay? And then meron din daw siyang ceiling, no? So pwede tayo maglagay ng ceiling actually dito to hide yung ating mga joists. Depende na lang kung gaano ka kapal yung drywall na gagamitin o yung material na gagamitin, no? Okay? Ayan. And then, sabi spacing ng ating joist is 300 mm on centers. Okay? So we have 300 mm. Okay, and then meron pa tayong partition wall. So pwede nating i-assume na meron siyang partition wall dito, no? So, or meron siyang may wall siya dito naka yan. Okay. So lagay lang natin ang label. So this is yung ating wall. Okay. Ito yung ating floor system. Ito yung flooring natin. Ito yung ating mga joist. And then ito yung ating ceiling. Okay. So yan yung cross-section ng ano natin. Kung titingnan natin ngayon sa direction na to, ngayon, no? Sa longitudinal direction, what will be our figure? Okay, so pwede sabihin natin ito yung ating ayan. So ito pwede sabihin natin ito yung joist natin. Okay? Sabihin natin nakapatong siya sa girder. Okay? Then yung ceiling natin is ito na lang, no? Ayan. Okay? And then yung ating flooring, of course. Then yung ating wall, no? Pero as ano siya, as pressure siya. So parang inano siya, distribute na siya dun sa whole area natin. Pero in reality, halimbawa, dito siya nakalagay sa, halimbawa, ito yung wall na yun. No? Pero hindi natin consider na as point load siya. Parang consider natin siya as one uh, as pressure load dun sa buong area ng floor natin. Okay? So, i-revise ko lang yung ano para iba yung itsura niya. So, lagay na lang natin na parang ganyan na loading siya, no? Pressure loading na siya. Okay? So, again, this is our wall. In pressure siya. Then we have our flooring. Okay? And then ito yung joist natin, yung required natin i-design. And then ito is a girder. And then ito yung ating ceiling. Okay? Yung nakalagay na ceiling joist, siguro para to help yung stability ng ceiling natin, pwedeng maglagay dun sa corners ng mga joist, no? As support. Kaya meron siyang nakalagay na uh, weight for ceiling joist. Okay? Ayan. So, yan yung system natin. And ang sinasabi natin dito na 3.6 meters is actually yung buong length ng joist natin. Okay? So ito yung 3.6. Lagyan natin in mm na, no? 3,600 mm. Okay? So, yan. So, yan yung diagram natin ng mismong beam natin. So, ang kailangan natin gawin, first and foremost, is to identify yung loading natin. Okay? So, punta tayo sa loadings. Okay? So, loadings tayo. So, since sa timber is ang kino-consider natin is service load lang tayo, working stress lang tayo, sabihin yung total load na kailangan i-carry niya will be equals lang dun sa summation ng dead load tsaka ng ating live load. Okay? So mula dito sa figure natin o dito sa previous slide, we have 500, 250, and 480. Tapos meron tayong 2,000. Okay? So let's indicate that here. So meron tayong um, yung values natin are again 500 plus 250 plus 480 Pascal para dun sa dead load, and we have 2,000 Pascal para dun sa live load natin for a total weight of or unit pressure na 500 plus 250 plus 480 plus 2,000. We have 3,230 Pascal. Okay? So, in Pascal siya. So, ibig sabihin, as area pa siya. Okay? Pagbabalikan natin itong diagram natin, as full area pa siya. Ang kailangan natin is yung tributary lang na i-carry ng isang beam natin. And that tributary pertains dito sa section na to. No? So, kumbaga, dun sa ano natin, dun sa diagram natin, itong portion lang na to, yung i-carry ng mismong ano natin, uh, mismong joist natin. Okay? And that width is equivalent to how much? That is equivalent sa yung spacing ng joist natin, which is 300 mm. Okay? So we can multiply our weight. So 300 mm. So again, si Pascal is 3,230 Newton per meter squared. Then multiply natin ng kanyang tributary width, okay, na 0.3 meters. Okay? So meron tayo ngayon na weight is equals to times 0.3, 969 Newton per meter. So itong weight na to will be the one applied dito sa beam natin. Ito yung mismo yung beam natin, di ba? Ito yung pinaka-beam natin, yung joist na design natin. So, dyan natin i-apply yun. So, using a free body diagram, so ito yung girder na isa. And then, ito yung girder sa kabila. Ayan. Then we have our uniformly distributed load. Okay. Na WT is equals to 969 Newton per meter. Then we have here a length of 3,600 mm. Okay? So yeah. So yan na yung simple beam lang pala yung meron tayo. Now that we have that, we need to check kung ano yung property ng 80% stress grade Apitong. Apitong. Okay? So ang kailangan natin kunin is yung allowable bending natin, allowable shear, and yung ating modulus of elasticity. So let's go back dun sa ating table. So ito yung reference table natin and we need to find Apitong. Okay? So this table is 80% stress grade. And then itong table na to, yung first column natin is for bending. Okay? Second column is for modulus of elasticity. And last column is for shear. Okay? So yun yung kailangan natin mga values. Hanapin natin sa Apitong. In high strength, hindi siya high strength, no? Moderately high. So, saan ba? Hindi din siya moderately high. Si Apitong po ay ito. Okay? Ayan. Let us close up lang. Yan, si Apitong po ay ito. So, yung gagamitin nating values sa kanya are 16.5, 7.3, tsaka 1.73. Okay? So, mapapansin niyo yung unit. Yung sa first column is MPa. Yung sa modulus of elasticity is gigapascal and then megapascal. So, we have 16.5, 7.31, and 1.73. So, let's have that dito sa ating, yeah. So, we have 16.5 MPa. We have 7.31 gigapascal. Okay? Sa modulus of elasticity pala yun. So we have 7.31 GPa. Then we have a shear na 1.73 megapascal. Okay? So dito mo ngayon i-compare yung values ng actual bending shear values natin. Okay? And meron tayong nakabigay sa problem na allowable na deflection as L over 300. 300? Yes, 300. No? So, babalikan natin later yan. Okay? So, let's start first with analyzing it for flexure. Okay? For flexure, we have the formula FB is equals to 6M over BD squared. So, para sa rectangular, yan yung formula niya, no? And then si M natin, may formula yan na, since this is a uniformly distributed load lang, okay? Ang formula natin is WL squared over 8. Okay? All over BD squared. Okay? Pero ang problem natin is we don't have the value for the cross-section. Kasi yun nga yung de-design natin. So, what we can do is to analyze or equate natin yung mismong allowable or actual value ng bending natin sa allowable value ng bending natin. Equate natin dun sa allowable. Meaning, yung makukuha nating dimension should be yung pinaka-minimum na magbibigay ng gantong stress. Okay? So, we need to focus on that. So, since we have that value, we can look for the value of BD squared. And for floor joist, okay, ang karaniwang practice for floor joist is ang kanyang width is always 50 mm. Okay? E makikita niyo yung cut sa ano no, may gumagamit tayo ng 2 by 2, 2 by 3, 2 by 4, 2 by 5, 2 by 6. Laging naka 2 inches yung kanyang width, no? So, more or less yung cut niya, nagbabari lang yung depth. Ito lagi siyang 2 inches. Okay, yung ginagamit natin. Kaya meron tayong 2 por 2, no? 2 por 3. So, yan po yun. So, assume natin na yung B natin is 50 mm na o 2 inches. And then C D squared na lang yung magiging unknown natin. So, let's substitute. Yung FB natin, again, is 16.5. Megapascal, pwede din siyang gawing Newton or Newton per mm squared. Okay? So, kailangan natin ng uniformity ng units. Okay? Then we have 6 times yung weight natin is in Newton meter. Okay? So, pag kinonvert natin sa mm yung ilalim, gagawin lang natin, multiply lang na, divide lang natin by 1,000. So, we have 0.969 Newton per mm. Okay? Then yung W, L squared natin is 3,600 mm squared. I-square natin to. And then we have 8 times 50 mm d squared. Okay? So, when we calculate for d, may makukuha tayong value sa kanya. Okay? So, let's calculate. So, pwedeng 6 times 0.969 times 3,600 squared all over 8 times 50 times 16.5. Okay? So, d squared pa yun. So, square root nun, we will have a value of 106.85 mm. Okay? And kapag ano tayo ng dimension for joist or for wood, no? Ang increment niya lagi is 1 inch or 25 mm. So, pwede natin i-say na yung D natin is 125 mm in diameter. Okay? So, ngayon, ang itatry nating dimension is according dun sa na-calculate natin. So, let's try na dimension na 50 mm by 125 mm. Okay? So, yan yung initial section natin. So, tatry natin yung actual bending stress niya na 6M BD square. So, that is 6 times yung ating W na 0.969 Newton per mm times yung ating 3,600 mm squared over 8 times 50 mm times 125 mm squared. Okay? So yung FB natin, upon calculation, is equals to 6 times 0.969 times 3,600 squared all over 8 times 50 times 125 squared. That is equals to 12.06 Newton per mm squared or 12.06 MPa. And we have to check dun sa ating bearing dito, bending dito. Ang bending stress natin is 16.5. Since ang FB natin is less than dun sa FB natin, therefore, okay siya sa bending. Okay? Okay siya sa bending. Right? Next. Shear naman tayo. Test for shear. Okay? So since meron na tayong na-try na isang section, yun na din yung section isunod natin na itatry, no? So try 50 mm by 125. So parang checking of adequacy tayo in shear. Okay? So kay shear, FB is equals to 3 halves V over BD. So yan po yung formula niya. And ano ba yung magiging value ni V? Magiging pong value ni V mula dito sa ating uniformly distributed load is kung ano yung magiging value ng support natin. And equal po yan sa this is yung ECL niya, okay, na W times L. So para suportahan ng support yan, we should have WL over 2 as our maximum shear para dito sa buong beam natin. Okay? So, sabihin dito sa sabihin natin that is equals to W over times L over 2. So, we have 3 halves times WL over 2 BD. Okay? So, ito maging 3/4 times yung value ng W natin, 0.969 Newton per mm, times yung length natin at 3,600 mm, divided by yung BD na lang natin, 50 mm times 125 mm. Okay? So, 0.75 yung 3/4 times 0.969 times 3,600 all over 50 times 125. Our value of FB is equals to 0.42 megapascal. And we need to check, no? Ang value ng FB natin is 1.73. So kung 1.73 siya, so less than tayo ng FB. So therefore, okay siya for shear. Okay? So pasado din siya sa shear. So sa strength requirement, pasado na tayo dun sa dalawa, sa flexure and sa shear. Okay? Ang susunod natin ngayon is to check dun sa deflection and sa uh, lateral stability natin. Okay? So, let's continue solving. Letter C is for deflection. Okay? Sa deflection, sabi ang allowable natin is L over 300 or yung 3,600 natin mm, divide natin sa 300. So yung allowable natin is how much? So 12 mm ang pwede nating deflection. Okay? And according dun sa binigay nating table sa previous slides, so sa deflection, we have a table, pwedeng pag-referan kapag we are looking for values ng maximum deflection. And ito yung condition natin, no? Yung kanyang loading is uniform distributed lang. So yung maximum deflection natin can be calculated using this formula, no? 5 over 384 times W L4 EI. Okay? So let's go back dito. So we have maximum deflection is 5 over 384 WL to the fourth over EI. Yung E natin is yung modulus of elasticity na kuha natin sa table. And yung I natin, that is moment of inertia. And for rectangular section, ang formula niya is BD cube over 12. So, sa-substitute lang natin yun dito. So, we have 5 times yung W natin is 0.969 Newton per mm. Okay, length na 3,600 mm. The fourth all over 384 times yung modulus of elasticity natin, ang value niya is 7.31 gigapascal. Okay? So 7.31, pwede siya maging 7.31 times 1,000 Newton per mm squared. So megapascal, no? So 1,000 ang difference nila. Times yung I natin na B na 50 mm, D na 125 mm, cube, tapos divide natin ng 12. Okay? So, pag kinalculate natin, that will be how much? 5 times 0.969 times 3,600 to the fourth. Yung 12, pwede natin i-multiply na sa numerator. Then 384, 7.31 times 10 to the 3 times 50 times 125 cube. We have a deflection value na 35.623 mm, which is greater than dun sa allowable natin. So, ibig sabihin, therefore, siya ay fail in deflection. Ibig sabihin, hindi natin pwede gamitin si 50 by 125 kasi magfe-fail siya sa deflection. Okay? So, ang gagawin natin is, therefore, adjust depth, no? Adjust natin yung depth. Okay? So, dadagdagan natin yung lalim nung ano natin. So, again, increment of 1 inch lang tayo. So, next natin is try 50 mm by 150 mm. Okay? Pero ang check na lang muna natin is yung sa ating deflection kasi yun yung hindi tayo nagsasatisfy, no? Again, yung allowable natin as calculated is 12 mm. So yung ating max will be equals to 5 times 0.969 times 3,600 to the fourth times yung 12 na nasa ilalim all over 384 times 7.31 times 10 to the 3 times 50 times 150 cube. Okay? So check natin kung ilan yung magiging maximum deflection natin. Okay? So yung max is still large, no? Dun sa ating ano pa din, greater than dun sa allowable pa din natin. So, para makuha natin yung papasa dun sa allowable, gawin natin, baliktarin natin yung process, no? I-equate natin na yung maximum natin equals dun sa allowable natin. Okay? So, magiging 12 mm is equals to 5.969, 3,600 to the fourth times 12 all over 384, 7.31 times 10 cube times 50. Then gawin nating unknown yung depth natin to 3. Okay? Then upon calculation, makukuha natin D is 5 times 0.969 times 3,600 raised to 4 times 12 all over 384 times 7.31 times 1,000 times 50 times yung 12. Okay, may makukuha tayong value. Then, i-shift cube root natin. O i-cube root natin para maging D lang siya. So, makukuha tayo ng value na 179.65 mm. So, again, increment of 25 mm o 1 inch. So, lumampas na siya ng 175. Say natin ng D is equals to 200 mm. Okay? So, ang kasunod natin gagawin, tatry natin ngayon si 50 mm by 200 mm. Okay? Again, i-check natin yung maximum deflection. We have 5 times 0.969 times 3,600 raised to 4 times 12. Inuulit ko lang po yung formula natin. 384 times 7.31 times 10 cube times 50 times yung 200 cube natin. Okay, so ano yung magiging value ng maximum deflection nun? So, i-calculate nyo lang. So, 5 times 0.969 times 3,600 raised to 4 times 12 all over 384 times 7.31 times 10 to the 3 times 50 times 200 cube. No? The answer will be 8.697 mm, which is less than dun sa allowable natin. So, therefore, safe for deflection. Okay, so safe na siya for deflection. Ngayon, mangyayari dun sa ano natin, dun sa shear and sa ano natin, sa flexure. So you have to verify also. Okay? So, pag chinek mo yung sa shear sa ano, sa flexure, okay? So copy na lang natin yung itong portion na to. Then gagawin lang natin uh, value ng D natin is 200, no? Pero as you can see, nasa denominator yung D natin. So pag laki ng value niya, meaning liliit yung value ng stresses natin. So ibig sabihin, mas papasa pa siya for flexure, and shear. Okay? So, kahit without even checking or writing yung mismong value, makikita natin na pasado na siya, no? So, pero papakita ko lang din yung actual value na makukuha natin. Okay? So, this is 6 times 0.969 times 3,600 squared all over 8 times 50 times 200 squared. So, that is 4.71 MPa. So, less than na siya dun sa allowable natin. So, okay. Okay. Dun sa FB natin, that is 3 halves WL. So, copy ko na lang yung nandun sa previous slide. So, ito yung value na yun. Ano? Papalitan lang natin ang value ng D, which is dapat siya ay 200. Okay, so ito yung value niya. And then, papalitan lang natin yung depth. Gawin natin 200. Okay, so 0.75 times 0.969 times 3,600 all over 50 times 200. We have 0.262 MPa, which is less than dun sa FB natin. Therefore, okay. Okay? So sa tatlong requirement, okay na tayo. For deflection, for flexure, and for shear, okay na tayo. Okay? Then last checking natin is for lateral stability. Okay? So for lateral stability, kailangan i-check natin yung L over B. Yung L natin is 3,600. Ang B natin is equal to 50. So how much is this? That is equals to 72, which is greater than 40. So let's go back to sa conditions natin kapag lateral stability. So ang kino-compare natin siya is sa 20 at 40. Greater than 20 siya, so hindi siya case 1. Hindi siya in between ng 20 at 40, so hindi siya case 2. So ang mangyayari sa kanya, greater than 40, so siya ay case 3. O ibig sabihin, laterally unsupported tayo, meaning kailangan natin maglagay ng bridging sa kanya. Okay? So, let's go back dito. So, therefore, siya ay laterally unsupported. Okay? Provide bridging. Okay? So, anong nangyayari pag sa bridging, no? So, halimbawa, ito yung ISO ng ating joist, no? Okay? Yung bridging natin, kung yan yung kabuuan ng length niya, again, halimbawa, lalagyan natin siya ng naka-across sa kanya. Okay? So, ito yung bridging natin. O yung blocking na tinatawag. Okay? And pag nangyari yon, yung original na length na ginagamit natin sa design, ang gagamitin natin ngayon is yung half na lang niya sa pag-check ng lateral stability. Okay? So, ngayon, kukuha ka ulit ng bago. L over 2B ka na ngayon. Okay? Kasi nag-half na yung length mo. So, this will be 3,600 over 2 times 50. Okay? So, that is 36 na lang. No? So, that is greater than 20 pero less than 40. Okay? Therefore, um, partially supported. Okay? And ano pag partially supported? Pag partially supported, you need to go back doon sa equation natin for case 2. Ayan. Meron ka ng reduction in flexural strength. Gagamitin natin tong formulang to. And then yung magiging value ng K natin, since we are a simple beam with uniformly distributed load, 1 over 90 yung K natin. Okay? So let's go back dun sa Slide natin. We have f prime b is equals to fb times 1 minus, formula natin is a wait lang, KL over B. Okay, so KL over B. Ito, KL over B. Okay, pero yung L over B natin dito, pertaining na siya dun sa 36 natin. Okay, kasi yun yung kinoconsider natin. So yung flexure natin na FB is originally 16.5 yung value niya, no? According dun sa table natin kanina. So 16.5 times 1 minus 1 over 90, yun yung value ng K according dun sa table, and then times 36. So F prime B natin is equals to 16.5 times 1 minus 1 over 90 times 36. Ang value na lang natin ngayon is 9.9 MPa. Okay? So kapag nakuha mo yung bagong reduced value ng bending strength mo, you need to check yung FB mo. And according dun sa previous slide, ang FB natin ay equivalent sa 4.71. Okay? So 4.71 MPa is less than dun sa F prime B natin. Okay? So therefore, save for flexure and lateral stability. Okay? So, pinaka-conclusion natin, therefore, use 50 mm by 200 mm. This is Apitong joist with bridging at midspan. Okay? So, yan po yung magiging conclusion natin for this problem. So, this is the answer. So, we need to provide 50 by 200 na joist na supported at midspan by A-bridging to satisfy all the requirement for our checking ng serviceability and flexure. Okay?